Okay.
Okay, go ahead.
Good afternoon to everyone online with us here today at this webinar. The next in our series of webinars that we're doing on the prize winners from the Academy's Excellence in Environmental Engineering and Science program and conference that we have every year. I want to welcome you on behalf of the Academy and on behalf of our speaker. Our speaker today, I think we're really lucky to have John Fraser with us, who is the Senior Vice President and Wastewater Practice Director with Carollo Engineers, who I believe are based in Denver, as is this project. John is the gentleman in charge of the wastewater practice, where he's in charge of tracking industry trends and also maintaining a team of wastewater engineers and scientists who have the expertise, knowledge to offer innovative solutions to all aspects of municipal wastewater intensification practices, energy reduction and production activities, and also sustainability practices. I'm not sure. I think John's been there for quite a few years, and he's the guy who was project manager on the facility that's the featured presentation today. So we'll let him fill in the blanks on that when the time comes. And what we expect to do is have roughly 40 to 45 minutes of presentation by John. And then we'll do a Q&A session. And as you've probably seen on your screens, there is a block on the side, a chat block. So if you have questions as they come up, feel free to jump in and put your questions in. We'll get them queued up and answer them once John is done with his component of the program. So that being said, rather than me carry on, I'll hand you along to John. Hey, welcome, John. We look forward to your presentation. And
hey,
congratulations on being the winner.
Good morning and good afternoon to everyone that's online, and thanks, Burke, for the introduction. We're actually not headquartered, Carollo, in Denver, although we have a relatively big operation here. We're headquartered out in the San Francisco Bay Area. And for those of you online, you may know us as a heavy presence in the west of the U.S. and then throughout Texas and the Sun Belt states down into Florida. But we are doing some work in other places. A few years ago, opened up a Chicago and Great Lakes office, and then just recently, in the last month or so, opened up a Washington, D.C. office as well. So we're able to serve more and more agencies throughout the country every month, and that's good news. But wanted to talk to you a little bit today about the Robert W. Hite treatment facility. So how I thought we could go through this is first giving you a little bit of background on the Metro Wastewater Reclamation District out in Denver themselves, take a look at the Robert W. Hite treatment facility, the approach that this agency's taken to improve their nutrient removal and reduce nutrients to the South Platte River, look specifically at the project that was honored to be awarded the grand prize in design this year from the Academy, the South Secondary Improvements Project, talk a little bit how that project used 3D CAD during both design and construction and the benefits of that, some of the repurposing and rehabilitation elements of the existing process, take a quick look at how the plant is currently performing, and then I have a quick video that gives us a tour of the facility that you all may be interested in. So if any of you have traveled out to Denver, this is an aerial photo of Denver. You can barely make out the mountains on the left side of your screen here, just the foothills beginning of the Rockies. And what's shown in color is the service area. They have 6 basins, drainage basins within this district, and multiple connectors. So if you need to get your bearings straight, you've probably at one time or another hopefully flown into the Denver International Airport. That's out on the east side of town. The downtown skyline, you can see the Rockies in the background there with a beautiful bright sunny day and the skyline, and that's kind of where that sits on the map. And then if you've ever had a chance to get out here and see a concert at the famous Red Rocks, that's on the west side of their service area for this particular district. So hopefully that helps everyone get their bearings straight and remember, if they've traveled out to Denver, where these features are. With respect to the treatment facilities, before I get into that, this whole service area is about 715 square miles, and it's a regional facility district that has 38 connector agencies, total of about 1.8 million customers throughout this entire service area. They operate 2 wastewater plants. Brand new plant that was just opened this year, started treating wastewater maybe 3-4 months ago. 24 MGD total capacity there with the ability to expand up to 50 MGD, and they call that their northern treatment plant. And that serves some of the drainage area up on the north side of their service area. The facility we'll talk about today is the Robert W. Hite Treatment Facility, and that is their large facility. This is the largest wastewater plant west of the Mississippi all the way to the coast of California. So it's relatively large at a 220 million gallon per day capacity. So if I zoom in a little bit more on Denver, you can see DIA out here on the right-hand side, downtown in the center there. I traced the South Platte River, and in Colorado, the South Platte River flows north, eventually joins up all the way out to the Mississippi River. And where the river takes a big bend north of town, that's where the RWTF treatment facility is located. And that particular facility serves about 1.6 million of their 1.8 million customers. So let's take a quick look at the facility. This is an aerial photo of the plant, and of course you can see the South Platte River bending around the plant. You can see their effluent location discharging into the river. And let me give you a quick tour of the plant. This particular plant has two secondary treatment plants on one site. The north secondary plant consists of 12 activated sludge aeration basins, 12 clarifiers. And the old south secondary plant, which is a pure oxygen activated sludge plant prior to this project, had 8 aeration basins, pure oxygen, and 10 secondary clarifiers. Of course, there's a central solids handling that handles solids from each side of the plant, and a primary treatment and preliminary treatment in this part of the facility. So the original plant was the north plant. It was constructed in the mid-60s, and it was constructed to remove BOD, TSS, and provide disinfection. At that time, there was not a big concern about nutrients to the waters of the U.S. This is an aerial photo that the agency dug up from their archives from 1967, right after the startup of the new facility. You can see the 12 activated sludge aeration basins, 12 clarifiers, a blower building, and at that time, the extent of their solids handling facility. Solids handling at that time was done through incineration, and then ash and other material was stored in lagoons for final disposal. And this is the Headworks primary treatment at the time. South plant didn't exist in the 70s, and it was constructed in the 60s, and it was constructed in the mid-1970s, again, just for BOD, TSS, and to accommodate a capacity increase as the agency acquired more connector agencies from the region. And this is a photo from 1977 that shows the original north complex and then the new south complex with central digesters for solids handling, anaerobic digesters. You can see the pure oxygen activated sludge aeration basins here and surrounded by the 10 secondary clarifiers. In the early 1990s, nutrient criteria began to get more stringent on the South Platte River, and they modified the north complex to provide nitrification and partial denitrification. And they combined the effluent from the pure oxygen south facility and the modified north facility to meet a seasonal effluent ammonia somewhere between 9 and 13 milligram per liter, and a combined effluent nitrate of about 16 milligram per liter. And that was an improvement over no removal of nutrients under the former configuration. And this is an aerial photo in 1993 of the facility after the nitrification modifications were made. You really can't tell too much. Most of the modifications were internal modifications and the addition of a second blower building to be able to accommodate the air demand for nitrification. The sheds at the bottom of the photo are compost sheds. At that time, they composted about 10% of their total biosolids, and the remaining portion of the biosolids is applied on the Metro Grow farms and some other farms out east of Denver. So in the early 2000s, the district knew that they were going to face more stringent discharge criteria on the South Platte, and they had to plan for their strategy for nutrient reduction. At that time, they were putting out an effluent from the north facility that could nitrify, so their ammonias were generally less than 2 milligrams per liter, but only partial denitrify, and so they're putting out about 12 to 17 milligrams per liter of nitrate. And that was combined with effluent from the South Plant. Now, the South Plant, being a pure oxygen activated sludge, did not remove any ammonia. And so the ammonia that went out of this plant was essentially the ammonia that came in the raw wastewater, somewhere between 18 and 24 milligrams per liter. But at the same time, they didn't produce any nitrate because they weren't nitrifying. So the combined effluent was somewhere between 9 and 10 milligrams per liter of ammonia. They split the flow approximately 50-50 on an average day between the North Plant and the South Plant. So their blended effluent was about 50% of each of these effluent water qualities. So somewhere between 9 and 10 milligrams per liter of ammonia, and somewhere in that same range of nitrate when they were blended. But neither of those numbers were good enough to meet the future criteria that was coming on the South Platte River, so the district began planning a strategy to improve the nutrient reduction at this facility. And they decided the first step had to be improvements in the north secondary complex. And the reason they needed to do that is because it was clear that the only way to modify the south secondary complex for nitrogen, for improved nutrient removal, both ammonia and nitrogen, was to take at least half of the capacity out of service at a time to make those modifications. In order to take half of the capacity out of the service, they needed to gain capacity in the north facility. So that's what they did first, and that design started in about 2004 and finished up and then was succeeded by the second step, which was replace the pure oxygen facility with a BNR facility capable of nitrification, denitrification, and even modifications in the future for phosphorus reduction. So one of the interesting things that came out of this plan was developed, the design, in about 2004 for the North Complex. And in 2004, the industry was beginning to think about side stream treatment as a big benefit to our treatment plants, but there wasn't a whole lot of facilities that were practicing side stream treatment. Today, side stream treatment is a major part of many agencies' game. They understand that if they have to meet a nutrient criteria and they can remove that in a concentrated form from their return streams if they have anaerobic digestion, then it's much more cost effective. But this was kind of relatively early in the development of side stream treatment process, and the district elected to use a process called CaRRB. Now, some of you may or may not have heard of CaRRB. There's a lot of talk about Animox-based side stream treatment, and CaRRB is an aerobically based side stream treatment that essentially means Centrate and RAS re-aeration basins. And I'll show you what the CaRRB looked like in the north complex, and then I'll show you how CaRRB was incorporated into the south secondary complex as well. So the reason that CaRRB and side stream treatment in general is attractive to the industry is the cost-effective nature of it. This agency looked at expanding the north complex by adding 2 more aeration basins and 2 more clarifiers. Their clarifiers are 30-foot diameter in the north complex and about a 2 million gallon aeration basin. So the cost of that to gain 18 MGD was about just under $40 million. And if you do that on a unit cost, about $2.25 per gallon of capacity increase. They compared that to side stream treatment, which they could gain 22 MGD of capacity at a cost of about $21 million. So that equates to just under $1 per gallon. So we're looking at about a 50% capital cost savings by doing what they needed to do in side stream treatment rather than mainstream treatment. And that number, I think, is generally reasonable, about half the cost for most other agencies across the country to use side stream versus mainstream treatment if you have the opportunity. So I would encourage everyone to be looking at side stream treatment if they have nutrient challenges in the future, because it can be a very cost-effective opportunity. So this is an aerial photo, a little bit grainy, of how they incorporated CaRRB into the north complex. They constructed 4 CaRRB basins in the area that was actually available in the north complex where aeration basins were not currently constructed. And this is what those 4 basins look like. They're essentially parallel. I'll show you the flow pattern in a second. And this is an aerial photo of the 4 CaRRB basins after they've been constructed. The odd-numbered CaRRB basins match up with the odd-number aeration basins up on the top of the page, and the even numbers on the bottom of the page match up with the even number aeration basins. And so the advantages of CaRRB as a side stream treatment is they're able to partially nitrify the centrate return. And in this case, because all of the centrate was treated, all of the centrate from the entire plant was treated in the north complex only, there was an imbalance when compared to normal plants with the ammonia load from centrate that comes to this north plant. So this CaRRB treatment for side stream was very beneficial and important in this case. CaRRB not only partially nitrifies the centrate, but it generates nitrate for denitrification in the anoxic zones of the BNR facility. It's kind of equivalent to the function of internal mixed liquor recycle. So where a normal plant might use a rule of thumb of 300% internal mixed liquor recycle for denitrification, this facility only has about 200% IMLR because the CaRRB basins provide the rest of the nitrate to be denitrified in this process. Also in CaRRB, it runs off a RAS feed. So RAS is generally about twice or a little bit higher concentration than the mixed liquor in the aeration basins. So because they're running at 6,000 milligram per liter, the size of the CaRRB basins required for nitrification are significantly smaller, about half of the size of conventional treatment. And this also allows the agency to reduce the mixed liquor in the aeration basins so that they can reduce the solids loading on the secondary clarifiers. They're secondary clarifiers for the capacity limiting process at this particular plant, and anything they could do to reduce the loading or improve the performance of the clarifiers was necessary. The other big benefit of the CaRRB side stream treatment is essentially we're growing nitrifiers in a very high ammonia concentration environment with the centrate as the substrate. And therefore, I like to call them super nitrifiers that are grown there. The nitrifier population is very strong, robust, and high, and that is fed back into the mainstream process, which bio-augments the performance of the mainstream process. I'll give you an example. The mainstream was designed for an aerobic SRT of about 4.3 days, and this agency, after they put CaRRB online, tried to see where the bottom was, and in the dead of winter ran the aerobic SRT down to 3.5 days without a breakthrough of ammonia. And that represents about a 25% reduction in SRT over what they were designed for, and we do believe that some of that reduction is definitely due to the bioaugmentation properties of a side stream treatment in this manner. So that's all kind of a setup for the grand prize winning project, the South Secondary Improvements Project. So let's take a quick look at that. The first thing that the agency had to do in order to modify the South Secondary Complex from pure oxygen to BNR activated sludge was to demolish the compost buildings to make room for the new facility. So after those were demolished, they were able to construct a new BNR air-activated sludge plant. And you can see the size of this is about 3 times the size of the pure oxygen aeration basin. And that makes sense because pure oxygen runs at somewhere between 1 to 1.5 days SRT biomass, and BNR runs somewhere between 4.5 to 6 days. And so generally, we're looking at 3 to 4 times the aeration basin volume when moving from pure oxygen to BNR activated sludge. And you can see that with the footprint difference here. At the same time they were building the new BNR activated sludge, they had to modify the west complex for HiPOS. Those pure oxygen basins were no longer needed, and that space was valuable for some of the new facilities that had to be constructed to make the whole system work and perform at the right level. Once that was completed and half of the facility was online, they then took out the east HiPOS and made the exact same modifications on the east side and are currently now running with all the facilities in service. So in order to accomplish this, we have to take a stepwise approach moving into the project. The first step was to demo the composting buildings to clear the site and prep the site both with some pre-excavation and some utility relocations in order to construct the new facility. And that began in about January 2010. In March 2010, a couple months later, we can see that the compost buildings are largely removed. In September 2010, they began working on the excavation, pre-excavation of the area that the new facility would be constructed in. And by January 2011, just about the time that the larger project was bid, the site was cleared, all the utilities were relocated, and some pre-excavation had begun to expedite the construction of the aeration basins in this area. So what was built in the area? Let me give you a quick tour of what was built. The facility has a capacity of 114 MGD out of the total 220 at this site. And it consists of 6 parallel aeration basins. And these are single-pass aeration basins. There's a conventional, probably urban legend that BNR aeration basins have to be multiple pass to make it easier for mixed liquor return through the wall, make them more cost-effective. And that really isn't the case. Any configuration of passes is acceptable for BNR. This particular design is a single pass, and there are several examples of single pass BNR basins throughout the country. So that's the aeration basins. The head part of the aeration basins is the anoxic zones for nitrate reduction. And in fact, there are some anaerobic zones as well in this design that allow for future biological phosphorus removal. CaRRB was also incorporated into the South Secondary, and the CaRRB was for the side stream treatment of the ammonia return from dewatering of anaerobically digested sludge. And in this case, we started with a clean slate, so we were able to locate CaRRB in an ideal position for the best, most cost-effective construction of the facility. And it happened to be at the tail end of the process, and I'll show you the flow pattern momentarily. We created a west mechanical building, and this supported the cost effectiveness of this facility. Not only were all of the aeration basin common walled together, but the main mechanical complex was all in a single building in 3 parts. The first part in red is the primary effluent pump station. They did have to lift into this plant because the hydraulic profile of the existing plant had the primary treatment at a lower elevation than secondary treatment. So they were lifting into the pure oxygen basins. They had to lift to catch the hydraulic profile that existed in the existing plant. The second main portion of the west mechanical building is the blower building, and this is where all of the blowers, air supply equipment for the complex is housed. In between the pump station and the blower building, where almost all of the load for this facility resides, is the electrical power supply. You can see that in yellow. That also added to the cost effectiveness, all in the same building. The wiring costs, the amount of copper, the line losses, all were dramatically reduced by placing that building in between the 2 highest loads. There was a second electrical building on the east side of the complex to supply some power needs on that side. The facility includes mechanical equipment and piping utility galleries. A west gallery that's located right alongside the west mechanical building, a central gallery, and an east gallery, and that houses all of the equipment so that in inclement weather, cold times in Denver, they're able to do all of their work inside on this facility where most of the piping and mechanical equipment resides. So this is a schematic of the liquid treatment process, and I think what we want to point out here is the flexibility of the process. The aeration basins were designed in 8 zones. The first 4 zones are unaerated, so it can serve as either anaerobic for phosphorus reduction or anoxic for nitrate reduction. Zone 5 is a swing zone, and what they often do is run Zone 5 aerobically in the winter when they need a little higher SRT, and anoxic in the summer to help improve their effluent nitrogen profile. After the aeration basins, we flow to the existing plant where we modified the facilities to include Stage 5 post-aeration, and the Stage 5 is there to support a future Stage 4, and so you'll see a kind of a common 5-stage, maybe we can call it Barden flow, but 5-stage process for phosphorus and nitrogen reduction here, with a second anoxic stage in the future and a Stage 5 aerobic polishing prior to split to the clarifiers. So this again is the unaerated zones. One thing that's important in unaerated zones for good treatment efficiency, well, there's 2 things I'd like to point out. One, you can see a little bit of a hydraulic discontinuity here. That is actually flowing over the baffle wall for this unaerated zone. You can see the mixer here and a little bit of the flow pattern on top of that zone. And so one thing that's important is not to trap scum in the basins, not only for maintenance issues, but also scum is an area where filaments like to grow. And if we want to manage filament populations within the treatment plant, we want to make sure that we don't trap scum. The other thing you can see here is a definitive line between the final anoxic zone and the aerobic zone. You can see that there's no back mixing or poisoning of the anoxic zone with oxygen, and that's very important in efficient nutrient reduction. So Zone 5 is the swing zone, and then of course the future Stage 5 and the CaRRB side stream treatment. The other feature is that the internal mixed liquor recycle and the CaRRB effluent come through a return channel that allows us to feed that liquor into either the first, second, or third zone, depending on the goals we're trying to meet for nitrogen and phosphorus. So this is a look at the facility in a 3D CAD view. This is what comes straight out of the model from our 3D CAD files. Of course, it's 114 MGD capacity, $150 million overall. This piece of the complex cost about $134 million. The footprint is 700 feet long, so it's all one structure, about 350 feet wide in the 6 aeration basins, and the aeration basins are 20-foot sidewater depth. About 74,000 cubic yards of concrete was used to construct this single structure. The primary effluent pump station, located right here, consists of 5 56 MGD pumps. Each is 450 VFD-driven motors. On the end of the basins, there are 12, 2 per basin, 25 MGD, 75 horsepower mixed liquor return pumps that bring the mixed liquor back to the head of the facility. And in the blower building, there's 5 single-stage, 29,000 CFM, 2,000 horsepower blowers, and we'll take a look at those in a second. I think one of the very compelling and interesting things about this facility was the cost. At $150 million for 114 MGD, that's about $1.32 per gallon of capacity. The national average for secondary treatment capacity is somewhere between $2 to $4 per gallon. So this facility far undercosted the national average, and part of the reason was related to all of the Commonwealth basins that we've built, the common mechanical building, the straight piping galleries that allowed us to be more efficient with the piping and mechanical equipment, all contributing to the lower cost of this facility compared to others. So with regard to flow pattern, primary effluent comes into the wet well that's located at the head of the primary effluent pump station and then is lifted into the head of each of the 6 aeration basins. Return activated sludge is pumped from the 10 clarifiers into the head of the aeration basins in a separate feed line. RAS is also put into the CaRRB side stream treatment along with Centrate, and really the RAS is the biofuel, if you will, the biology that allows us to nitrify the Centrate in the side stream treatment. The effluent from the Centrate treatment and the mixed liquor return all combine in channels that run back to the head of the complex and then allow us to distribute that flow either at the head of the plant with the primary effluent and the RAS or into the various zone compartments. Most of the project and much of the cost was in the new South Aeration complex, but some of it was also in modifying the existing facilities. So that all of the secondary clarifiers were rehabbed, first the west side. A new stage 5 was constructed and a splitter box to those 5 clarifiers, repurposed inside of the existing basin, and new RAS-WAS pump station. And this modifications and repurposing was repeated then on the east side of the facility after what you see here on the screen was started and operational. One of the elements that was really important for this is the use of 3D CAD. I know this is a little grainy, but this is the 3D rendering of the facility as we envisioned it on the site. And this is an aerial photo when the facility's finished, and we can see the 3D image captured, very realistically how this facility would sit on the site, look and feel to the operations crew. And the operations and engineering team at Metro got a lot out of the 3D. It expedited design. They were able to visualize and see what the facility would look like, and it was very accurate to the final end product. So this, for example, is the 3D CAD renderings of the mixed liquor return pumps in the east gallery and the piping. And this is a photograph of the finished facility for mixed liquor return in the east gallery of the actual plant. Right down to the struts and pipe supports that you can see here that you can also see here in the rendered 3D image. This is a rendered image of the primary effluent pump station with the 450 horsepower motors, the open design of the dry pit and the discharge piping from the pumps. and then this is the actual facility after it's been constructed. So very realistic view of what the agency will get, all the way down to the small mechanical equipment that was also designed in 3D and rendered so the operators could understand how they can move around the facility and access the equipment. And then, of course, the actual finished product looks very similar to what came out of the CAD. The 3D was also used during construction, particularly the concrete construction. So all of the pours as proposed by the contractor were incorporated into the 3D CAD file, and we could virtually build all of the concrete pours on screen with the contractor to determine appropriate sequencing, a more efficient activity base. So the other thing that was done was some repurposing, and particularly of the existing HiPOS basin. This shows the 5 secondary clarifiers and the pure oxygen aeration basin. You can catch a corner of the 3D image of the new activated sludge complex. And in this pure oxygen system, there's a feed channel and then 4 high purity oxygen basins on one side of the feed channel with mirror image 4 basins on the other side for a total of 8 basins. So this is a close-up of that, and what was done was removing one of the pure oxygen aeration basins and in its place constructing stage 5 aerobic polishing and then a gravity mixed liquor split box. Prior to the construction of this box, the split of mixed liquor to the secondary clarifiers was done through modulating gates off of a common channel. And they had wide variations of splits to each of the clarifiers because the modulating gates were chasing their tail and hard to control. So they moved to a definitive gravity split, and they have exact split now between all the clarifiers. In 2 of the other basins, the RASWAS pump station was constructed, and that is in a central location. There was essentially no space around the site on the perimeter of the clarifiers to build RASWAS pump station, and this represented the best location for RASWAS because all of the clarifiers kind of come into a central location here. And so this facility was repurposed for the RASWAS. And they even left decommissioned and left available for future stage 4D nitrification, the final HiPOS basin. And all of this was repeated mirror image on the other side of the facility. So this is a photo of the repurposing construction. You can see there's rehab of the clarifiers going on. This side of the plant on the east, on the right side of the screen, is operational still, with all of the aeration basins operational as well. And they're modifying both the RASWAS pump station, stage 5, and the mixed liquor split box. Here's a picture of the work that was done in repurposing to create RASWAS pump station. These are the suction pipes for RAS, and they're pouring the slab that the RAS pumps will sit on. And this is a shot of the work being performed on the mixed liquor split box in the repurposed basin. These walls were walls that were existing from the existing complex. This is the finished product of the RASWAS pump station, and you can kind of see the line where these columns are. This was one HiPOS aeration basin. This was a second. And you can see how this provided a great space with ample room to work around all of the pumps, discharge piping within this area for a very nice RASWAS facility. And this is a look at the gravity mixed liquor flow split box repurposed into one of the high purity oxygen basins. There are 5 active splits in this and a future split for a future 6th clarifier. And again, mirror imaged on the other side. This box, I think, handles about peak flows of about 150 MGD. They also modified the clarifier mechanisms. This was important because the clarifiers were a capacity limiting step in the process, and they had small or no energy dissipating inlets in their old clarifiers. You can see the riser pipe type clarifier mechanism. You can actually see the lines on the floor where the riser pipes touch the floor and were sucking up the biosolids out of the bottom of that clarifier. These are the new clarifiers that were constructed, and one of the most important features is the maze-type energy dissipating inlet, EDI. Well, it was also combined with suction header sludge collection mechanisms. This is a view of the maze EDI, and it shows what this is all about. This is the influent well, and the flow comes in and has to travel through a tortuous path to get out of this EDI into the flocculation well. And so that dissipates the energy as it hits the baffle and then has to go around the baffle to go out the next set of baffles. And you can see that the net openings in the first ring are small. They get a little bit bigger in the second ring and finally bigger still in the third ring. And what that does is it reduces the velocity of the mixed liquor as you go through the maze. And the end result of this was before this energy dissipating inlet was installed, they could run about a max of 26 pounds per day per square foot. And now they can run up to about 42 pounds per day per square foot. That's how important energy dissipation is in the inlet. It shows the maze EDI, the flocculation well, and the suction headers that were put in. And this is the EDI in action. You can see some of the turbulence here, and you can kind of see that it slows down through the maze into the flock well, and we have really good flocculation in the flock well. These are the new clarifiers in the South Secondary Complex after they were put in service, and they have the same mechanisms and EDIs placed in them. And the effluent quality is relatively high, somewhere normally between 10 and 15 milligram per liter TSS. And many places can do better than that, but these clarifiers are pushed pretty hard at this facility. So they're highly loaded clarifiers, and they still easily meet the effluent criteria. So let's take a quick look at the plant performance. This is a full-scale operation of the plant after it's been online. You can see one aeration basin out of service. One side stream CaRRB basin is in service. 2 of those are out of service when this photo was taken, and 5 of the 6 aeration basins are in service. These channels here are the mixed liquor return channels, and in between these basins is where the air piping is to feed air into either of the parallel contiguous aeration basins. So the NPDES permit for this facility has a summertime maximum number, so this is the lowest number they have to meet at 1.75 milligram per liter of ammonia. And their nitrate plus nitrate or NOx value that they have to meet is 8.68. They have an 85% goal to beat that, to operate at only 85% of their limit or less. So that's about 1.5 milligram per liter of ammonia, 7.5 milligram per liter of nitrate, and 1 milligram per liter of phosphorus when they try to do phosphorus removal. With all this facility operational and treating its max capacity, they run about under 1 milligram per liter of ammonia, under 5 milligram per liter of nitrate and nitrate, and under 1 milligram per liter of phosphorus. And this is a chart that shows the effluent quality through a year, through a 6-month period. The nitrate is the blue up here, and you can see that they never violated their permit. They got a little close at one time of the year as they went through the transition between summer into fall, brought that back around by adjusting their SRTs, and normally run less than 5 milligram per liter out of this plant. The total phosphorus is shown in green, and they're normally well below 1 milligram per liter when they're balancing both phosphorus and nitrogen removal. They don't currently have a phosphorus limit, but they did want to test out and see what their performance looked like for phosphorus. The end result was about 4 million pounds per year of nitrogen removed from the South Platte River. And this is a look at the ammonia concentrations before the project went online. In 2013, they were up to somewhere between 10 to 15 milligram per liter of ammonia in the combined effluent. When they got a portion of the plant online, that dropped somewhere between 4 and 10, and then after the entire plant was online, they're consistently below 2 milligram per liter. Same thing with the total inorganic nitrogen, the TIN. They were generally, before any of the facility came online, in the 12 to 18 milligram per liter range. When half the facility went online, they dropped that down to 10 to 15, and when the full facility came online, they're generally running at 5 milligram per liter or below. And again, the result, 4 million pounds of nitrogen out of the South Platte River based on this process. The other interesting thing that Metro has done, they've done a lot of pioneering things, this agency, including their side stream treatment processes and many other things, but they also have a focus on energy savings and through what I'll call LODO operation or LODO operation, and this kind of represents that. You can clearly see the aerobic zone here, and they've reduced their DO residual in this zone somewhere between 0.5 and 1.5 milligram per liter. And they do this through direct ammonia control and also by making sure their set points are as low as possible to get the treatment they need. They've actually, you can see here, turned the air off of the final aerobic grid of aerobic zone to save more energy. So they're operating with anaerobic zone and anoxic zone with much of the volume up front, and then also at the tail end of the process in an anoxic condition. With that operation, they're able to treat 114 MGD because we ran the facility up to its max capacity to test it out, and they could get less than 1 milligram per liter of ammonia, about 6 milligram per liter of nitrate, and less than 1 milligram per liter of phosphorus, all at a very low energy cost through low DO operation. So I have a little video that I want to show, then we'll open it up for Q&A. I am going to get to that video right now.
The Metro Wastewater Reclamation District serves 1.8 million customers over a 715 square mile area in Greater Denver, Colorado. The district operates 2 wastewater plants, the larger 220 million gallon per day Robert W. Hite treatment facility and the new 24 MGD Northern Treatment Plant. Since the 1970s, the Robert W. Hite treatment facility has been using pure oxygen-activated sludge to treat nearly half its daily flow. While a state-of-the-art treatment process in its day, changing nutrient requirements and regulations are driving public agencies like the district to find new answers to treatment challenges. The district has been planning for greater nutrient removal since 2004, when it hired Carollo engineers to design modifications to the North Secondary Complex. As part of that project, Carollo introduced a novel CaRRB side stream treatment process capable of removing 85% of return ammonia loads at half the cost of conventional treatment. CaRRB also supercharges the main process through bioaugmentation. Several years later, Carollo again helped the district with design and construction of the South Secondary Biological Nutrient Removal, or BNR system, to replace the now obsolete pure oxygen technology. The South Secondary improvements required initial demolition and clearing of composting warehouses to make way for the new BNR-activated sludge system. Carollo modified half of the pure oxygen facility at a time so the plant could remain in service. The new 114 MGD South Secondary Treatment Complex consists of 6 parallel aeration basins, filling the space of 3 football fields. These massive basins took 74,000 yards of concrete to build, enough concrete to fill a sports arena 125 feet deep. The aeration basins receive oxygen from a large blower building capable of producing 145,000 cubic feet per minute of air. 5 high-speed, high-efficiency single-stage blowers are driven by 2,000 horsepower motors, sending air to more than 53,000 membrane disc diffusers. Specially designed walls and anaerobic anoxic zones provide nitrogen reduction and, in the future, will remove phosphorus from the wastewater stream. The new process offers the flexibility to operate under a variety of advanced configurations, allowing the district to accommodate current and future treatment requirements. The facility also includes a state-of-the-art 280 million gallon per day pump station that lifts primary effluent to the new aeration basins. Each of the 5 56 million gallon per day pumps is powered by its own 450 horsepower motor. The main power distribution center is the hub of the plant's central nervous system. Miles of wiring is routed through a roller coaster of cable tray to supply power to treatment processes, monitoring equipment, and even the lights and climate controls for the administration buildings. Piping and equipment galleries feed each aeration basin and controls flows to treatment zones to create high-quality effluent for reuse or disposal. To save on capital costs, Carollo repurposed the old oxygen aeration basins to serve as a new sludge return pump station, which splits return flow to the rehabilitated clarifiers for further treatment. Prior to new plant operations in 2013, effluent ammonia ranged from about 9 to 15 milligrams per liter. After startup, effluent ammonia dropped to less than 1 milligram per liter. Similarly, effluent nitrogen ranged from about 10 to 20 milligrams per liter, dropping to just 3 to 5 milligrams per liter with the new facility in service. Simply put, the new B&R process has reduced effluent nitrogen discharge to the South Platte River by more than 4 million pounds per year. Besides a need and desire to protect the environment, the district's modifications are consistent with the 5 major trends in the wastewater industry, which includes nutrient reduction and recovery, energy conservation and production, intensification, sustainability, and community enhancement. In recognition for the district's stewardship of the environment and its innovative use of technology, the district was awarded the prestigious 2017 Grand Prize for Design by the American Academy of Environmental Engineers and Scientists. The extremely low unit construction cost of less than $1.50 per gallon provides an example for other Rocky Mountain Front Range communities who are faced with increasingly stringent nutrient requirements. And this project will serve as a benchmark for public agencies of all sizes across the country and around the world. At Carollo, water is our focus, our business, and our passion. Being part of innovative treatment projects like this affirms our commitment to our clients and our communities and helps us move closer to our goal of working wonders with water.
Okay, I'm going to go back to sharing my screen with everyone, and hopefully you saw everyone was able to see that video. And I think I can open it for questions. Anybody has any questions? We can take on anything you'd like to know.
If any of the attendees have any questions, you can just type it in the window to the left there, in the chat window.
There aren't any questions yet.
There we go. Thank you, Peter.
Good. So let me take the first question about the delivery method. This particular facility was delivered under design bid build, so it was not an alternate delivery. But there was an owner's advisor involved because of the size of this, and there was also several parallel projects going on the site at the same time. So they did use an owner's advisor. The owner's advisor team was Black & Veatch and Brown & Caldwell, and Carollo worked alongside the owner's advisor during the preliminary design of the facility. So the district got the expertise and brain power of all 3 of those firms working together in preliminary design. And it was set up in a way that as we moved out of preliminary design, Carollo was comfortable in advancing that forward all the way through final design, bidding, and then construction management through the 5-year construction facility. but that was all done under a conventional design bid build. The next question is related to were there any changes in the solids dewatering and the disposal systems? So those changes are being performed in separate projects. So the answer is yes, there will be. There's an ongoing parallel project that hasn't been bid yet. It's currently in design to modify their dewatering facilities. So the big issue with biological phosphorus removal is impacts to solids handling. And those impacts to solids handling are kind of two-fold. The first impact is a reduction in cake solids. And if I get this right, we usually see a 2 to 5 point reduction in cake solids when biological phosphorus removal is implemented when it wasn't implemented before. And there's a long history of why that is, and there's some ways to overcome that. One of the ways is additional polymer use, and additional polymer generally goes up by maybe about 10%. And so those are big impacts, especially the lighter cake or less concentrated cake, which results in higher truck traffic. And these guys dispose of their biosolids about 26 miles east of town, so it's a big cost. So right now what the district's working on, and the second impact is struvite. So struvite's a problem when they try to run biological phosphorus removal. Dewatering's a bigger challenge. And so they're working on a struvite recovery project, and they're working on a new dewatering project that will accommodate the reduction in dewaterability by changing the types and the throughput of their dewatering machines. So there was another question of peer auction. I don't see it popping up on my questions, so let me take the ones that are on my screen. One of those is, what was the engineer's estimate at the time of the bid? So you could either say we were either really bad estimators or the bid climate was really favorable. And I think the bid climate was really favorable. This was bid in about 2010, at the end of 2010. And so our estimate was about $212 million. And that was also estimated not only by Carollo, but also by Black & Beach and Brown and Caldwell, who we all thought that this would come in about 210, and it bid at $143 million. So it's about an $85 million savings off what we thought we were going to pay. And that was mostly attributable to the very, very favorable, the recession and the favorable bid climate at the time. So I have 3 questions.
If you go over, John, if you go over to attendee chat in the left-hand corner, then you can see the additional questions. So you can just get out of that and then go over to attendee chat. Do you see that?
Yeah, attendee chat. Okay. Let's see what else is up here. The horsepower voltage, for the voltage for the 2,000 horsepower is, I'm probably going to get this wrong. I want to say 2160, but that's stepped down. But they are high horsepower motors, so it's higher than 480, whatever the step is above 480. I'm sorry I don't have that, but I can figure that out for you. These are the formerly Turblex, now then Siemens, and now I believe Roots has picked up that line of single-stage centrifugal blowers. Let's see. So the residual management is they have thickening in DAFs and gravity thickeners for primary sludge. They have then anaerobic digestion and centrifuge dewatering with ultimate disposal through land application and reuse. And it's really not disposal, it's reuse. Let's see what else we've got here. I'm just going down the list one by one. Well, a question about the repurposing of the aeration basins. And you know, the interesting thing about repurposing when you're doing something like a basin, what we were really repurposing was some of the concrete, 3 of the concrete walls, and the space. It's the space that we needed. So there was some surprises when we pulled that down. We did inspect the inside of the tanks, but we had to enter in confined space gear and flashlights, and so our inspection was relatively limited, and we felt like the condition was adequate for reuse of those walls. When we got down, we found that the concrete loss and the exposed aggregate was pretty significant, and so we did have to add I think it was about $125,000 change order to recoat and repair some of the interior walls. But in the end, the facility turned out pretty good, but there was a few surprises along the way. So it said, the next question is from Peter, flow recycle from an aeration zone back to the anaerobic zone. And I think this question is related to, you know, that brings some dissolved oxygen back to the head of the plant into the unaerated zones, and that reduces the efficiency of those zones. So that's accommodated by 2 things. First, it's a relatively long channel that is not aerated, that the mixed liquor is returned. And so that depresses much of the oxygen in the return stream. The other thing is that they do like to operate by turning the grid down very low or almost off on that last zone, so that they can also depress the oxygen and not poison those return zones. But a lot of the impact is related to the long return channel and no aeration or mixing in that channel, so they're able to keep the DO low in those unaerated zones. So the next question by Victor is the disinfection. They're currently using HiPO and bisulfite for disinfection, but they're testing other chemicals. They're testing peracetic acid, and they're thinking about possibly going to peracetic acid. They've talked about UV, but the power demand for UV is pretty high, and they're trying to look for other alternatives. You know, it's hard to say. Dennis's question is $1.50 per gallon, and part of that benefit is that we're reusing quite a bit of existing facility. What would the cost be if it was new? I think we could have beat the national average of $4 per gallon, and the reason why is we get quite a bit of economies of scale at this size, and that allowed us to use these common wall aeration basins, allowed us to not use a campus-style facility, but rather a single-structure facility. And all of that added to the cost-effectiveness, and including both the bid climate at the time and also the fact that there were some existing facilities in place, like the clarifiers, that were reusable without building new facilities. But I still think that the tricks that were used here are beneficial to the industry to take heed of, and note that a single structure is more cost effective than a campus style plant if you can do that. So the next question, are there more projects like this currently being designed or in progress? And I would say, I don't know what the like this means, but the industry in general is forced with meeting across the whole country. There's nobody that's free of this, meeting more stringent nutrient criteria. So as all of the industries have to, dischargers have to go to more stringent nutrient criteria, they're looking for creative ways to do that biologically. A lot of agencies looking at ways to reduce their energy consumption and looking for ways to be more sustainable and reduce the amount of chemical use. So I think right now is a great time to be in this business, and there's a lot of work to create projects like this around the country. There is another project that's a conversion of pure oxygen activated sludge in Sacramento, California. Actually, it will be a little bit larger. That complex will be about 180 MGD. And that is under construction or just beginning construction right now and won't be completed for several more years. But pure oxygen plants in general have challenges in meeting nutrient criteria, so those who operate pure oxygen are examining their future discharge needs, their future water reuse needs, and determining if and how those plants can serve them in the future. Net zero energy. Kathleen asked about net zero energy. My feeling on net zero energy is that the challenge for us in this business to get to net zero is to find ways to reduce or eliminate aerobic treatment. And I know there's a lot of things we all can do in our facilities to move us closer to net zero. But as long as we have aerobic treatment and rely on aerobic treatment, it's going to be very challenging, I believe, for the industry to reach that goal. So this agency is doing, so what does anaerobic treatment in the mainstream mean? Does it mean anaerobic as in digesters? The challenge with that historically has always been the strength of the wastewater. Municipal wastewater is generally too dilute to support cost-effective anaerobic mainstream treatment. But at the same time, turning our air down and relying on more unaerated zones is something the industry has to take a serious look at. And this agency is one agency who's done that and reduced their power cost quite a bit by trying to get their air as low as possible, putting as many zones as possible into unaerated. They're actually finding better performance, and across the country we all are finding better performance under this operating mode because of different biological pathways that are being discovered. Our biomasses are very resilient, and we put them in an environmental condition that we don't think they'll work, and by golly, they seem to work just fine and adapt to those conditions. So, I think that we're moving that way. Thinking more and more about reducing our air and moving away from aerobic treatment is really something that's going to be necessary for us to get there. Thanks, Kathleen, for asking that question. So Tina asked what other side stream processes were considered. At the time in 2004, Animox-based processes were not in widespread consideration around the country. I think Strauss was using Animox-based back in that time period, but it hadn't really translated to the U.S. Now, 10 years later, there's a lot more interest in Animox-based. So really this CaRRB system, there were so many benefits associated with the fit of CaRRB into the facility that the district operations staff, and the other thing is operating CaRRB is very much like operating air-activated sludge. It's the same bioculture. If you know how to operate an aeration basin, you can operate CaRRB. So this district, as their first venture into side stream treatment, elected to use CaRRB, and that's pretty much all they looked at because other options weren't available except physical chemical options. And there were actually some agencies that had been using CaRRB, New York NDPE, I got that right, NDEP, had tested a CaRRB-like facility for many years at 26th Ward and some of their other plants successfully. So this wasn't necessarily brand new, but it was perhaps the largest application at its time of CaRRB. So I also want to note that this district is looking at Animox-based side stream treatment right now, and in fact moving forward. And the reason why is carbon management. They've looked at their carbon profiles, and in order to, they have a goal not to add any external chemical, any external carbon. So that's a sustainability goal, and they're going to do everything they can to avoid external carbon. So using an Animox-based side stream treatment allows them to reduce ammonia and nitrogen and also not burn up any carbon that's available for phosphorus removal. So CaRRB will still stay in service to serve as aerobic SRT, but they'll also be supplementing that with Animox-based side stream treatment. So we have a question about, is the Maze ADI proprietary? And yes, it is currently proprietary. And the individual who patented that is someone we worked with back in the late 90s, Sipping Zoe, who did a lot of modeling and developed the Maze EDI. This particular agency, because we worked closely with Sipping, was not subject to the royalty associated with the patent on the EDI. But to be honest, we have been designing other EDIs that have a lot of the same principles of serpentine, tortuous pattern out of the inlet, and increased opening sizes, decreased velocities as you go through the EDI that are more target baffle type EDIs that are not proprietary, and they've been installed and are working with similar results. But the Maze, I endorse that particular product. It's been a great product for this agency, and you can see by the 26 to 42 pound solid loading increase that they got, how effective it's been. So I don't know if I've drained out all of the questions or not. Maybe Marissa and Bert can help me to see if I've got any other questions, but I think I've covered most of them.
I think you got them all.
Yeah, very, very well done. Thank you, John. And to our audience, thank you for stopping by. Hope it was productive and useful to you. And be sure to check out the Academy. We have more webinars coming up in the next few months, all of which are award winners from the E3S conference. So that being said, thanks again, John. I think we'll all tune out. Have a great day.
Thanks to the Academy and everyone out there in the industry.
Thank you, and we'll have the recording link up as soon as it's available. Thank you so much.
All right, thanks. Hopefully this was a great success for you all.
I think so.
Thanks, John. Bye-bye.
Okay, thanks.